Satu. Mulai.
Good afternoon, everyone. My name is Bayu, and with me is my partner Nicholas. Today, we will be presenting our research on evaluating CNN and KNN for tumor detection accuracy in medical imaging. Medical imaging is an essential cornerstone of modern medicine, crucial for diagnosing and monitoring diseases, especially tumors. Integration of artificial intelligence has led to the development of powerful automated tools that can enhance the accuracy and efficiency of this diagnostic process. So, for our paper, we are submitting in EACT for our conference of choice. So moving on, our research focuses on two distinct but significant algorithms. The first is a traditional machine learning method, K nearest neighbor, otherwise known as KNN. And KNN is an instant-based learning algorithm that classifies data points based on how close they are to existing. Its simplicity and effectiveness on smaller datasets have made it a popular choice, especially in situations where large amount of labeled data are not readily available. However, KNN faces a major challenge with the high-dimensional data, typical of data images, a problem known as the curse of dimensionality, which can degrade its performance. On the other hand of the spectrum, we have convolutional neural networks, or CNNs, a powerful deep learning approach that revolutionized medical image analysis. Unlike KNN, which often requires manual feature selection, CNNs automatically learn hierarchical patterns directly from the images themselves. This ability to extract complex features from simple edges to intricate tumor structures allows them to achieve exceptional accuracy even when with patterns that traditional models might miss. However, this power comes at a cost. CNNs demand very large training datasets and significant computational resources, which can limit their use in environments where these are scarce. Therefore, the purpose of our paper is to conduct a direct comparison between KNN and CNN for tumor detection. We will evaluate their strengths, weaknesses by focusing on key point metrics such as accuracy, computational efficiency, and overall practical application. Our goal is to provide a clear analysis that can help researchers and medical professionals make informed decisions when selecting the right AI tool for their specific needs, balancing the trade-offs between performance and available resources. Now, moving on to the methodology. For our methodology, we used a dataset of MRI brain scans categorized into tumor positive and tumor negative cases. We implemented several pre-processing steps to standardize the data, and all images were filtered to the JPEG format and converted into an RGB color space. So for the KNN model, images were resized into 128 times 128 pixels and converted into grayscale. On the other hand, CNN models were resized into 64 times 64 pixels. And finally, we split the data into 80% for training, 20% for testing using stratified sampling to ensure balanced distribution. So regarding our implementation, this is our architecture. So for our KNN, we used an implementation of histogram of oriented gradients, otherwise known as HOG, to extract features from the grayscale images. We tested multiple K values from 1 to 9 to find the most accurate neighborhood size. Our CNN is a sequential model with 3 convolutional blocks, each followed by a max pooling layer to reduce dimensionality. We also used a dropout layer to prevent overfitting and use a softmax activation function for the final binary classification. And moving on to the results will be explained by my partner Nicholas.
Now, on the model performance. Now, for our results, the KNN model performed impressively. The optimal performance was achieved with a K value of 1, resulting in an accuracy of 97.5%. The confusion matrix you see here shows the model's strong ability to correctly classify both tumor and non-tumor cases. The detailed classification report confirmed these findings with precision, recall, and F1 scores, all consistently around 0.975. This demonstrates that a traditional machine learning approach with effective feature extraction, like a hawk, can be a very strong baseline. The CNN model, however, achieved even better results, as you can see from the graph. Over 10 training methods, the training and validation accuracy steadily increase, while the loss decrease, indicating that the model learned effectively from the dataset. Across all F1 metrics, CNN was superior. It achieved a final accuracy of 98.8%, a precision of 98%, and an F1 score of 98.6%. The near perfect log-out score of 0.9983 further highlights its exceptional ability to distinguish between the two classes. Now, next to the conclusion. In conclusion, this experiment compared a KNN model with Hawk features against a CNN for brain tumor classification. Both models performed exceptionally well. The KNN approach proved to be a powerful and viable method, achieving high accuracy and demonstrating that traditional machine learning should not be overlooked. However, the CNN model delivered a marginally, yet consistently superior performance across every metric we measured. This leads us to conclude that for this specific task, the CNN ability for advanced hierarchical feature learning make it more effective and robust solution for classifying brain tumors from MRI scans. Thank you for your attention. We are now happy to presentate this presentation. Thank you.
Thank you for your attention.